Good time of the day, everyone. Welcome and thank you for joining us for this webinar by the GIF Education and Training Working Group. The webinar of today is titled Modeling UO2 Fission Gas Release Thresholds in BISON. On the next slide, I'll just give a few housekeeping elements and then we will start the webinar. So please use the listen through your computer option to ensure you hear us well. If you have any technical difficulties, please check the Zoom support website. Most importantly, if you want to ask a question, use the Q&A option. I will show in a second where it is. This webinar is recorded. The recording will be shared as well as the presentation given on the public GIF website. And a survey should be sent to you at the end of this webinar. Please take the time to take this survey to help us improve our webinars. So on the next slide, you have at the bottom of your screen a Q&A pane. You can click this button. It will open you a pop-up where you can type your question. You can ask your questions all along the webinar, and at the end of the webinar, our moderator will take your questions and the presenter will answer them. So now I would like to introduce on the next slide our moderator for today. Dr. Patricia Pavier is the National Technical Director of Molten Salt Reactor Program for the U.S. Department of Energy, Office of Nuclear Energy. She has been an active member of the GIF Education and Training Working Group since its inception. She was actually the first chair of this group, and she is now the webinar lead for the Education and Training Working Group. She has been instrumental in establishing the present series of webinars and keeps it flourishing with the energy and enthusiasm she puts in it. She will facilitate today's webinar and the follow-up Q&A session. And now I let Patricia introduce our speaker for today with the next slide. Thank you.
Thank you so much, Alexei, for the introduction. It's a pleasure to have Miss Kaylee Cunningham with us today. It's very important for me to have a student like her pursuing a PhD and participating in this GIF webinar series. So Kaylee is a first-year PhD student studying material science at the University of Florida. She's also a graduate research assistant in the Material Science Division at Los Alamos National Laboratory in the US. She is currently a National Science Foundation graduate research fellow as well. She holds a master's degree in nuclear science and engineering from MIT and a bachelor's degree from the University of Florida in nuclear engineering. Her work is currently focused on engineering scale computational modeling of ceramic nuclear fuel. In addition, she's a very talented person because she's as well an experimentalist. She's the 2024 first place American Nuclear Society Pitch Your Thesis contest winner. She was also recently named a Thomson Reuters Future Leader in Energy for nuclear energy advocacy work via social media. So thank you so much, Kaylee, and congratulations of your very brilliant path. It's really nice to have young people like you participating in this GIF webinar series. So without any ado, I give you the floor. Thank you, Kaylee.
All righty. Thank you all so much for having me today and for signing on whatever time zone you're in. I'm here in Los Alamos, New Mexico, and it is bright and early this morning. So I appreciate you all again for taking the time to sign on. So today we are going to talk about the work that I'm focused on for my PhD dissertation. And that is looking at the best way to model the fission gas release threshold for currently UO2 and in the future UN and UC nuclear fuels. And this work is being supervised by my PhD advisor at the University of Florida, Dr. Michael Tonks, and my research mentor at Los Alamos, Dr. Christopher or Topher Matthews. So I wanted to start off with a big picture idea of what our objective is here, and that is to essentially create a versatile tool for predicting the onset of fission gas release using the BISON nuclear fuel performance code. Now, starting with an overview of what fission gas release is, I know we have people with a wide variety of backgrounds logged in online today. Now, coming from the material science perspective, fission gas release is a mechanism we observe in nuclear fuel that starts in the grains of the fuel. So if we're looking at a UO2 fuel pellet on the microscopic level, that UO2 fuel pellet is going to consist of different grains because it's a polycrystalline material. So each of these grains, represented as hexagons here, are essentially individualized crystals within the structure of the material. And then I have highlighted in green here these grain boundaries. And these are essentially the boundaries that just separate these different crystals. Now, the fission chain reaction in these fuel pellets produces gaseous fission products like krypton, circled here, and xenon, circled here. Now, because these gases are noble gases, they're almost completely insoluble in the UO2 matrix material, or within these grains that I mentioned before here. Now, because they dissolve poorly, they don't really disappear and return back into the matrix. Instead, they diffuse towards each other and cluster together. Sometimes they'll cluster together to form bubbles like we just saw here, or the gas atoms migrate to the grain boundaries. And those grain boundaries act as almost like highways for these gas atoms to travel through. And that's because the crystal structure within each of these grains is separated by these grain boundaries. So it's essentially an area within the structure of the material that has no sort of obstacles for these gas atoms when they're moving through the material. Now, as gas atoms start to accumulate on these grain boundaries, they'll cluster together to form intergranular bubbles on the boundaries. So essentially they're diffusing or migrating from the center of each grain to the grain boundaries. Now, eventually, when we have an influx of gas atoms migrating to these grain boundaries, all those gas atoms will start to collect within these bubbles until those bubbles get so big that they interconnect to form or coalesce to form tunnels, which eventually results in gas release of these atoms to the fuel's surface. So in summary, this fission gas release mechanism is essentially a process where fission gases that are almost completely insoluble are produced via nuclear fission and then are eventually expelled from the surface of the fuel. Now, another important mechanism that I want to touch on before we dive into the work that we're doing here and why it matters is a process known as resolution. Now, resolution occurs all because of fission fragments, which you can see a fission fragment pictured here in red. Now, that fission fragment on occasion can collide with bubbles full of gas atoms. And that collision essentially transfers energy from the fission fragment to the gas atoms within the bubble and gives them just enough energy to overcome that energetic barrier so that they can escape the bubble that they're in, resulting in the gas atoms becoming resolved or returning to the material matrix that we see in here. Now, these gas atoms, when they resolve or return to the grain and leave the bubbles, this can influence fission gas release by increasing the amount of release we have because we have more gas atoms available in here to diffuse to the grain boundaries and eventually transport out of the fuel material via those tunnels or bubbles coalescing into tunnels for that release process. But why does any of this actually matter? So understanding this gas atom diffusion process, the resolution of those gas atoms, and the resulting fission gas release process is incredibly important to keeping nuclear reactors safe when we're designing them. So for those of you that aren't super familiar with the nuclear industry, with nuclear reactors, I know we have some material science people here. The nuclear reactors are fueled by, typically light water reactors are fueled by these tiny uranium dioxide pellets that are about the size of a gummy bear. Now, those pellets are stacked up inside a metal shell, this metal cylindrical tube that we call in the industry cladding. Now, if we don't properly take into account this fission gas release process, that could lead to gases being released into this cladding space, so much so that the cladding could become overpressurized and potentially even rupture, which you can see pictured here at a few different temperatures, different pressurization testing of zircaloy cladding. That is the absolute last thing that we want to see happen in these nuclear reactors, because that could result in the release of fission gases to the environment. Excuse me. And that's the number one thing that here in the United States, the U.S. Nuclear Regulatory Commission is prioritizing, is preventing release of any sort of potential radiological hazard to the environment. So it's actually really, really important that we're calculating how much fission gas release is going to be released into the fuel rod to make sure that our reactors are staying safe, especially as we start changing designs of these fuel rods, moving into these advanced reactor designs. Now, to be able to calculate how much fission gas will be released, fuel designers in the nuclear industry have historically used the Vintanza fission gas release threshold curve. Now, this threshold curve is essentially a model that is entirely empirical, so derived from data, experimental data, that was published back in 1979 and predicts the rod average burnup and the axial peak fuel centerline temperature at 1% fission gas release, approximately, which you can see plotted here. This is the original Vintanza curve and the data that was used to calibrate or calculate it. And I should also note that it is the axial peak fuel centerline temperature. And this here is the equation that is used to essentially calculate at what burnup or what fuel centerline temperature you're expecting to see the start of that threshold, that 1% fission gas release. Now, it should be noted that a lot of these experiments here actually did not reach exactly 1% fission gas release. The data is actually pretty scattered between less than 2%, 1%, 0.5%, 0.2%. But the approximation that has actually worked fairly successfully for the last few decades is this curve produced by this equation here. Now, as I mentioned, this model is entirely empirical and makes several assumptions, starting off with fuel geometry. It assumes a standard light water reactor fuel shape, including radius as well as cladding or rod height. It also assumes the operating temperature of the reactor as well as the power level, and it only applies to roughly 60 megawatt days per kilogram of UO2. That, for those of you who aren't familiar, is a measure of burnup, which is essentially how much of the fuel we are using up when we are producing energy. Now, I want to point out, first off, for those of you that may or may not have noticed, that this curve only goes to about roughly 45 megawatt days per kilogram of UO2. Now, a few years after this was published, this curve was validated all the way up to 60 megawatt days per kilogram of UO2 for different experiments on UO2. So it was confirmed that that 60 megawatt days per kilogram is effective, but it was never validated beyond that. Now, another thing I want to point out about this 60 megawatt days per kilogram of UO2 is this diffusion curve. So stepping back for a second, diffusion is essentially the mechanism in which these gas atoms are migrating from the center of that grain that we saw earlier to the grain boundaries. The way that they travel, we call diffusion. Now, I want to point out in each of these sections that we've experimentally, which you can see from the data points here, each of these X's represents an experimental data point. This is xenon diffusivity or diffusion in UO2 fuel. Each of these kind of sections of diffusivity can be segmented into regions. So starting off first here, we have the fission gas intrinsic region. So this region highlighted here in green is essentially a high temperature region. So the diffusion rate, or how quickly the gas atom is moving from the grain to the surface of the material, is going to depend only on temperature in this regime. Now, if we highlight here the D2 regime, this intermediate temperature region, here the diffusion of the gas atom is going to depend both on temperature as well as fission rate, or, excuse me, going to depend on temperature as well as fission rate in this kind of middle of the road region. Now, this D3 region is arguably the most important for this application. This is an athermal diffusion region, meaning the diffusion of these gas atoms is only going to depend on fission rate. So the different interactions that are happening in the material while it's fissioning is the only thing that's going to affect this. So at higher temperatures, the gas atoms will move at the same rate as lower temperatures within this region. Now, if we pay attention to this region highlighted in orange here, the D3 region, this region begins or initiates roughly around 1300, maybe a little over 1300 Kelvin. If we look back at the Vintanza curve, 1300 Kelvin is a little over 1000 degrees Celsius, which is roughly where this Vintanza curve starts to reach an asymptote. So if we want to be able to push our fuels to higher and higher burnups with these advanced reactor designs, that's one of the goals of many that are designing fuel for these advanced reactors. This model does not capture that behavior. The athermal diffusion is not being captured by that threshold model. And that's a really, really big problem, because this athermal diffusion is something we've experimentally observed. So if we're not taking that into account with this Vintanza threshold, we're going to be missing some very important behavior. Now, the Vintanza threshold also assumes, as I mentioned before, fuel geometry. And this includes specifically a full fuel rod geometry. And that can be really challenging to extrapolate to rods with different lengths of fuel. So taller rods, shorter rods. For example, if we're looking at small modular reactors, we might see, or likely will see, shorter fuel rods. Now, the reason that it is so difficult to extrapolate this information from a longer fuel rod to a shorter fuel rod is because the localized burnup, temperature, and fission gas release, among other things, are not equivalent to full rod averages. Okay, so if we see a fuel pellet at the top of the fuel rod here, it's going to see a very, very different fission gas release, burnup, and fuel centerline temperature than a pellet towards the bottom of the fuel rod. Now, you can see the kind of trends here, how burnup peaks in the center, the temperature tends to peak towards the top, and fission gas release also tends to peak towards the top of the fuel rod. This makes it extremely difficult to convert from these longer fuel rods to much shorter fuel rods. So this Vintanza threshold cannot be very easily applied to rods with different geometries. Now, now our objective is to remove all of those assumptions that were made to essentially create a universally applicable and mechanistic UO2 fission gas release threshold tool that fuel designers can pick up and be able to use with relative confidence that we're capturing behavior better than the Vintanza curve alone for these advanced reactor designs. And then eventually the goal is to take the techniques we've learned by developing this UO2 threshold tool and applying them to uranium nitride and uranium carbide fuels. Now, why do we care about mechanistic? What exactly does that mean? So mechanistic models are generally based on theory, fundamental theoretical physics that is predicting how a model may change or deform. These mechanistic models are super important because they allow us to be able to forward predict how the fuel is going to behave at conditions that we don't have experimental data for. One of the biggest problems that we see in the US nuclear materials research fields, and likely abroad, is the amount of time it takes to actually conduct a nuclear fuel materials experiment. We are having or experiencing incredibly long lines to be able to, or wait times to be able to irradiate a fuel rod or a mini fuel rod or any sort of experimental material that needs to be irradiated. And then after it's been irradiated, so we're waiting several years for the fuel to be irradiated, then it has to sit in the reactor to be irradiated for several years, and then it has to come out of a reactor and cool down, likely before it's transferred to a hot cell for actual post-irradiation examination to take place. So this whole process can sometimes take 8 to 10 years to complete just one experiment. So our goal in using these mechanistic models is to be able to give a somewhat reasonable estimation of what the fuel is going to do without having to wait for these experiments to be completed. That's kind of where simulation instead of experiments comes into play. And in doing so, this can help better inform experiments in the future and allow us to better target what kind of experiments need to be conducted. And then those targeted experiments can give us a sense of, or allow us to quantify the uncertainty on the model. So this whole understanding or this whole framework of using a mechanistic model is actually going to be really, really important. Now, how exactly are we going to address that and implement a mechanistic model? This here presented these equations that represent these curves here were actually calculated mechanistically using the centipede moose-based multi-physics object-oriented simulation environment, multi-app structured code, and Centipede calculated from information that was produced via DFT density functional theory and molecular dynamics calculations, used information from those calculations to calculate the approximate diffusivity functions for each of these regions. And all of this work that you see presented here was published in a paper focused on xenon diffusivity in UO2 that my mentor at LANL, Dr. Topher Matthews, published. Now, when it comes to addressing the fuel geometry issue, another issue that I have not mentioned yet is the fuel's radius. Now, the fuel pellet's radius actually depends or influences the power level considerably for the nuclear reactor. So it can have a really significant influence on the fuel. But one of the ways that we can actually address this issue and normalize that out is by, instead of plotting just the fuel centerline temperature, adding a third axis to this threshold plot that we've been talking about to also model the fuel's surface temperature. And by pinning down the fuel centerline temperature, or Tmax, and the fuel's outer surface temperature, we're able to essentially normalize both of these power levels. Pinpointing both of them eliminates the power dependency as well as the radial dependency. Now, as I mentioned before, converting this full fuel rod data to one localized pellet is almost impossible. So taking these rod averages and trying to scale them to a smaller pellet that you can then scale to another shorter fuel rod is a very complicated process and very difficult to do correctly. And again, as I mentioned before, this is because all of these localized data points at these different fuel pellets are not equal because they depend on the axial location of the fuel pellet in the fuel rod. Now, if we instead, in our model a single fuel pellet, say we model this bottom fuel pellet here, then that bottom fuel pellet can be very easily integrated to produce the full rod's averages or calculations and give a better, more accurate estimate of what fuel designers can expect to see. So our focus here is modeling a simplified surrogate model of just the bottom fuel pellet. Now, getting into the work that was performed, I went ahead and put together a 2D RZ axisymmetric model of UO2 using the BISON fuel performance code. Now, I started with the BISON repository's Vintanza benchmark model that was constructed based off the FUMEX2 IAEA, or International Atomic Energy Agency's assessment. This FUMEX2 assessment was an international benchmarking initiative, FUMEX being an acronym for Fuel Modeling at Extended Burnups. And this FUMEX2 assessment specifically outlined the parameters that each different application or code that was used to benchmark essentially outlined exactly the input parameters to put into your model. And those you can see presented in the table here. And you can see the simplified single pellet model presented here with the cladding, that shell that goes around the nuclear fuel rod. And because this is a 2D RZ axisymmetric model, essentially what that means is that this is half of the fuel pellet here, and this half of the fuel pellet is essentially split radially down the middle. So if you spun this out in a big circle, then you would have a full three-dimensional cylindrical fuel rod. So that's essentially what we mean by this 2D RZ axisymmetric modeling. So this model was taken from the BISON repository and revised to include this mechanistic diffusivity that was calculated from the centipede cluster dynamics code. And then this model was then run with semi-empirical and empirical older default models for diffusivity, and the two were compared. Now, looking at the two that we compared, again, we ran mechanistic diffusivity as well as mechanistic resolution models for the blue curve here. And then the red curve was run empirically. This empirical model essentially included the default empirical experimental based models for resolution, fission gas release, diffusivity, all of those things. And then the data points that are presented here are the ones that were used, you can see here, in the original Vintanza benchmarking assessment. Now here you'll notice that the mechanistic model in blue is only about 60 degrees off from Vintanza, while the empirical model, is roughly 80 degrees off. Now, why is there a difference here? Well, first off, I want to highlight these regions here. These regions are representative of athermal diffusivity. That athermal diffusivity region varies from model to model. The empirical model has a different athermal diffusivity than the centipede mechanistic model. And that's what's causing the offset or shift here. But these downward curves, I do want to point out, are essentially this athermal diffusion behavior that the original Vintanza curve here dashed in black fails to capture. And I also want to point out that this empirical curve presents this athermal diffusion behavior at below 60 megawatt days per kilogram of uranium versus this mechanistic curve starts to see this athermal diffusion at just over 70 megawatt days per kilogram, which is important because we know that the Vintanza curve, as I mentioned before, was validated up to 60 megawatt days per kilogram of uranium. So because it's been validated up to 60, we are inclined to believe that the athermal diffusion behavior is occurring beyond 60 megawatt days per kilogram of uranium. And because it's occurring beyond that, and we're seeing that behavior represented in the mechanistic model, we have reason to believe that the mechanistic model might be slightly more accurate. But again, I am currently digging through literature, looking for the specific experiments that validated Vintanza up to 60 and some higher burnup experiments that we can add to this plot to see if we can validate this curve here. Now, another reason that we have this kind of offset between the curves, we see this offset up here that we see at this lower burnup region. This, I wanted to point out, is influenced by the initial grain radius in the fuel, or how large those hexagonal looking, they're not hexagonal in real life most often, but the hexagonal looking regions from the diagrams I was showing in the background section of this presentation. How large that grain is actually influencing this low burnup behavior. And then this higher burnup separation is partially influenced by the fuel's swelling. Then another difference or reason for the kind of offset here is the resolution in the material. And the resolution model, the differences between the mechanistic and the empirical models for this resolution. So I went ahead and performed sensitivity studies to see which curves would be, or which segments of the curves would be most heavily influenced by this resolution. So here you can see presented that the white section highlighted here is the empirical model that's in BISON for resolution, and then this dotted section here is the Satayawan model, which is mechanistic or mostly mechanistic. And you can see kind of the differences and the sensitivity as you scale that diffusivity of the white model dashed here versus the Satayawan model here. Throughout each region, scaling D1, that temperature dependent region, D2, that irradiation and temperature dependent region, and D3, the athermal diffusion region that is only dependent on the resolution, that is only dependent on the fission rate, is most heavily influenced by this resolution parameter. And this is likely because we see this more sensitivity observed in the empirical model versus the Satayawan model, likely because the white derived from the White and Tucker model assumes complete destruction of intragranular bubbles or bubbles inside the grain, while the Satayawan model instead actually takes bubble size and the reduced effectiveness of resolution as the bubble radius increases into account. So this essentially demonstrates that the resolution parameter is why these two curves are so different, and also highlights the importance of developing these mechanistic models. If we are vastly overestimating the onset of fission gas release, we're overestimating fission gas release, and as a result, are overestimating the pressure inside the rod. And so if we're manufacturing fuel rods that are much larger than they need to be, then that's an area of costs that we are spending more money on than we need to be. So just another caveat and the importance of these mechanistic models. Now, if we look at implementing these to construct a three-dimensional surface plot, this is a preliminary three-dimensional surface plot. Hopefully it's not lagging too much. Looks like it might be a little bit, my animation here. But this three-dimensional plot is essentially this surface threshold curve for each of these models that was generated. And this is our objective, is to be able to produce a curve like this where you can select a fuel surface temperature, a fuel center line temperature, and the gas release is going to occur. And here you can see the mechanistic curve in pink and yellow, kind of overlaying the empirical curve in blue and green. Now, that's a really cool, pretty plot, but why is it important? Why exactly does it matter? How do we know that it's accurate? Now, to be able to demonstrate how accurate BISON's mechanistic diffusivity model is, and how accurate BISON's fission gas release model is, a validation study was performed using an experiment from the Halden reactor, IFA 597. And this experiment is available in the Nuclear Energy Agency's International Fuel Performance Experiments database, and it was also a part of the IAEA's Fuel Modeling at Extended Burnup, or FUMEX2, international benchmarking assessment that I mentioned before. Now, IFA 597 was a high burnup integral rod behavior test that irradiated segments from the Ringhals 1 boiling water reactor in Sweden. This reactor was a commercial power reactor. So you can see essentially the process of the experiment. First, the fuel rods were irradiated in a base irradiation, i.e., to produce power in the Ringhals reactor, and achieved a rod average burnup of roughly 52 megawatt days per kilogram. And then PIE was performed later on at the Studsvik facility, calculating fission gas release to be between 2.5% and 3.3%. I chose to stick with the 3.3% because that was calculated by the Halden reactor facility. And the Halden reactor kind of team performed many of these fuel experiments looking at fission gas release, and all calculated fission gas release the same way, versus the actual team at Studsvik calculated fission gas release a little bit differently. So for consistency reasons, I stuck with the 3.3% here. Now, after the commercial base irradiation, these fuel rods were loaded into a nuclear test reactor, the Halden reactor. So these rods were refabricated and then irradiated in the Halden reactor for about 20 days back in July 1995, versus this commercial base irradiation was about 12 years. So a much shorter irradiation time for this experiment. And this experiment accrued an additional 2 megawatt days per kilogram burnup. And then a few fuel rods were removed, and then a third loading, some of the same fuel rods were added back into the reactor. These refabricated test rods and were irradiated January to May 1997, and accrued an additional 2 megawatt days per kilogram of burnup. Now, these end of this third loading, these fuel rods achieved on average roughly 15.8% fission gas release. Now, my objective here was to model solely the base commercial irradiation. And that's because this base irradiation reached a fission gas release percentage of 3.3%, which is fairly close to the 1% that we're looking for with this threshold, and that we're aiming to be able to validate these low fission gas release percentages using the BISON fuel performance code. So that's what I was focused on sort of benchmarking here. Now, this model was initially used in BISON to validate its thermal conductivity models. So it started off already in the repo, the BISON repository. And so we can see here the temperatures versus the linear heat rate actually matched up fairly well. And here you can see the mesh. We see the 2D RZ axisymmetric mesh. So we have a shorter, smaller fuel pellet that has a thermocouple inside of it, and then a smeared pellet mesh for the rest of the fuel, and then the cladding modeled here. This mesh, this kind of model here, is the one that was already in the BISON repo. And here you can see pictured just an idea of what the experiment looks like. We have fuel rods in here in this kind of test chamber. Now, the only problem with this benchmark model or validation model in the BISON repository is that it was used to calculate the rod average burnup and fission gas release percentage. And the rod average burnup actually lined up fairly poorly with the experimental result. You can see the 3.3% here, and BISON finishing after the 12 years plus a few days of radiation way out here. So I set out to repair this model, update it with the newer models and mechanical properties, et cetera, that are available in BISON. But I also, because we had here this shorter kind of mini fuel rod, this is a representation of the refabricated rod that went into the Halden reactor. I set out to model the entire roughly 4 meter long fuel rod that was used in the commercial base irradiation. And this is the mesh that I created, the smeared pellets here, and then the cladding presented here. Now, this another 2D RZ axisymmetric model of a full-length commercial fuel rod was modeled with the input parameters here Also presented in the FUMEX2 IAEA benchmarking assessment. So similar to the Mintanza model, but we're running an entire fuel rod. And so again, I modeled just the base irradiation of the fuel rod and ran with a fully mechanistic fission gas release model. So I used the Satayawan mechanistic resolution parameter, as well as the diffusivity, mechanistic diffusivity. Now, the problems with this IFA 597 original repository model, I was able to isolate them to the base irradiation of the power profile. Now, the base irradiation data was increased by roughly 6% to account for the fact that the total power was not presented in the data that was provided. The Ringgold's reactor facility recorded thermal power instead of that total power. But the original BISON model actually redundantly added a scale factor just under 6% to account for the difference in power. So after removing that, I was able to fix the burnup. Now, looking at the rod average linear heat rate, it was also presented as data over the refabricated rod length, not the full base irradiation fuel rod length. So I was able to rescale this power profile to a longer fuel rod length and take that scaled power profile and apply that to this full length fuel rod. And to acquire the full rod's axial peaking factors or axial peaking power profile, I was able to acquire that and kind of piece that together using some axial gamma scans of the fuel. So here you can see these kind of points here that average out to 1. So I was able to assume a flat profile for the shorter fuel rod that was already modeled in the repo, the refabricated rod, and the longer fuel rod, I was able to take a peaking profile from another document, a trace stability analysis that was performed for the Ringgold's 1 reactor. Now, taking that and constructing a third order polynomial function to kind of fit the data points that I pulled off of that, and using the BISON power peaking function model, I was able to kind of construct a peaking function for this fuel rod. And after implementing the power profile changes along with these mechanistic models for the fission gas release calculation, we actually got some really promising results. So here you can see presented in red the original model in the BISON repository. And then you can see the model that I revised, the new and improved model for this benchmarking study, and the 3.3% of this Halden PIE calculation. And here on the right, you can see just another sensitivity analysis just to confirm that Satayawan is that much more accurate than other semi-empirical resolution models in the BISON repository. So again, you can see the Satayawan model here in black with the Halden PIE data point here, and then the Vestchanov-Lazanin model here dashed in blue, and the Vestchanov-Tarasov model here dotted in orange. So if we kind of highlight where we are, I wanted to actually quantify how far we off instead of how far off we are from the experimental data point. And if we kind of zoom in there, we can see that our experimental data point at 3.3% is not too far off from the BISON simulation results coming in at 3.03%. This is only a difference of roughly 0.27% fission gas release, which in general is actually really, really good for fission gas release percentage modeling, especially at these lower fission gas release percentages. Now, currently, this kind of next step, I'm working on developing a simplified version of this full fuel rod model, identical to the simplified sort of surrogate Vintanza model, as this kind of final validation step. So I'm working now on creating this smaller, shorter, single pellet model of the bottom fuel pellet, and making sure that the data that is produced from that bottom fuel pellet can be integrated to calculate the full fuel rod, and making sure that the two match up. Now, kind of wrapping up here, walking through what we did and the kind of main points here. First off, starting up here, BISON's mechanistic model actually agrees fairly well with the Vintanza model, only about 60 Kelvin off, and the data used to construct the Vintanza model. The empirical model is a bit more conservative, assuming fission gas release happens a bit sooner, because we're about 80K below Vintanza instead of about 60K. And this is because the semi-empirical resolution parameter is that much more sensitive to gas diffusivity than the mechanistic one. Next, we look at the 3D surface plot. We created that and successfully normalized out the fuel geometry and power assumptions from Vintanza. Kind of the next step with this plot will be to take the data points from Vintanza and the Vintanza curve and co-plot them on the surface plot, just to be able to validate that we're doing things correctly. But of course, that will take place after we have a functioning simplified model that can confirm that the simplified model is an accurate representation of the bottom fuel pellet. Then with that 3D surface plot, we can kind of confirm that the plot is as expected, because we see the burnup varies with fuel centerline temperature and fuel surface temperature as expected, replicating the 2D curves. And then we can also see from that plot that the fuel surface temperature varies linearly with the fuel centerline temperature, which again is as expected from the equations. Now, with all of this, we were able to successfully develop a modeling technique to be able to produce a fission gas release threshold surface that may be used independent of fuel geometry or operating conditions, essentially normalizing out a lot of the limitations that are kind of baked into that Vintanza threshold model, the original two-dimensional threshold curve. Now, this modeling technique we were able to partially validate by constructing a model of the IFA 597 experiment base irradiation. Now, again, we still need to do that last step of comparing the surrogate simplified model to the full fuel rod's base irradiation. But once we've got that done, then we're able to say that we fully validated it. And looking a little bit further down the line with future work, the plan for the rest of my dissertation is to take this same modeling procedure and apply it to pelletized uranium mononitride fuel. So taking this 2DRZ axisymmetric and mechanistic model of uranium nitride and use that to calculate this 1% fission gas release threshold. Then validating that with experimental data in the literature and against the Wallenius threshold for uranium nitride, and then be able to create that surface threshold identical to UO2. And then the final thing that I'm hoping to get to by the end of my PhD is to be able to construct an identical model for uranium carbide, validate that, and then create a tool for uranium carbide. So essentially what we've done here is set up a framework for creating these three-dimensional, versatile, and mechanistic fission gas release threshold curves. And that is essentially the goal that we set out to achieve at the beginning of this presentation. Thank you all. So just some quick acknowledgements as I start to wrap up here. All the information from IFA 597 was acquired from the NEA's database, as well as that FUMEX2 report. This work was performed using Idaho National Laboratory's high performance computing resources. This work was financially supported by the National Science Foundation Graduate Research Fellowship Program. And any findings, conclusions, opinions, everything here are those of myself, and do not necessarily reflect the views of the National Science Foundation. And this work is partially funded by the U.S. Department of Energy's Office of Nuclear Energy. All righty, thank you.
Thank you. So I think on the next slide, we have the upcoming webinars.
Yes.
Perfect. I wanted first to thank you for this in-depth and fascinating presentation. And it's also inspiring to see how projects as the Halden Research Reactor project that was supported by the Nuclear Energy Agency can support further research. And it's really nice to see how young researchers are using these results to moving forward their research. So please join us on the upcoming webinars of the Education and Training Working Group, the next one being in July on thermohydraulics of supercritical water reactors. Then it's not here, but in August we should have a very interesting webinar on the non-electric application of nuclear heat and some results by the GIF working group that is focused on this topic. And then in September, we have a presentation by the GIF Proliferation Resistance and Physical Protection Working Group on the 3S interfaces for a pebble bed SMR. And in October, we should have a presentation on science for the safe disposal of nuclear waste. So please register, share the information with your network, and join us, as I think this webinar has shown. Those are fascinating and interesting talks to follow. And now I'll give the floor to Patricia to moderate the Q&A session. Thank you.
Yes, thank you very much for the great presentation, Kaylee. Extremely inspiring for the future leaders of nuclear energy like you are. Thank you again. So I see two questions for you, and I'm sure you can click on the Q&A box and you will be able to read them. So the first question is about the IFA 597. For the second loading, what does WODS refabrication mean? Does this affect the fission gas release?
Sure. So the second loading, refabrication essentially means that we are taking segments of the fuel out of the original long fuel rod and putting them into a smaller fuel rod. Essentially, actually, I should be able to go back to that slide. So if we look here, this kind of test rig here, the refabricated fuel rods are these smaller fuel rods inside this test rig. So again, we're essentially taking the fuel pellets from the original irradiation and chopping them up into smaller sections and taking those smaller sections or just a few fuel pellets and stacking them up inside these shorter fuel rods. That is going to influence fission gas release to a certain extent because we're looking at fuel that already has significant burnup, likely already has these kind of pathways or tunnels for the gases to escape. And looking at the different fuel geometry, because it's going into a smaller fuel rod, we likely will see more fission gas release. Hopefully that answers that question.
Thank you very much. Another question that starts really for thanking you with the inspiration that you presented today. This person is doing some research for HGR, which uses trisofuel. Would like to know whether fission gas release behavior in trisofuel is the same as in a pellet, because she's doing research on this subject. What's your opinion?
So I will say I'm not an expert in trisofuel. I'm not super familiar with it. I know fission gas release does occur, and because the triso, you're looking at the kernel, which is kind of like the core where the fuel is in the triso particle, and then that is encapsulated by inner pyrolytic carbon, outer pyrolytic carbon, and then typically silicon carbide kind of outer shell. The mechanisms themselves, you likely will see some fission gas release from the particle, because the particle, especially if your kernel is made of UO2, you are likely to still see fission gas release. It's still going to occur, but because you have multiple shells and then those particles are embedded within a material kind of graphite matrix, you're likely to not see as much fission gas release actually coming from the triso particles. That is an educated guess assumption. So like I said, I'm not an expert in trisofuel. You likely will see fission gas release, but how much of that is actually released from either your fuel pebbles or your fuel composites, I don't know.
Okay, thank you very much, Kaylee. Another question, actually, there are several questions. So the first one, are the computational grids of fission gases the same as heat transfer grids? But fission gases are usually produced from grains. This is a multi-scale question. Then we have, what is the computational grid you mentioned today? I mean, the PDE of fission gases. So we're going to stop there. It's already a lot.
Okay, yeah, I guess I'm not entirely sure what you mean by grids. Generally, the way that it is calculated is identical to the heat transfer for fission gases. Of course, there's the equations behind it. You're not just solving the heat transfer equation, you're solving a lot of very complicated mechanistic equations, but all of that is outlined on the Idaho National Laboratory's BISON website. If you search for SIPGRs is what it's called. I don't remember off the top of my head of what SIPGR stands for, but it is essentially the mechanistic fission gas release model that the BISON code uses to calculate fission gas release. Those equations are just solved for each meshing element, or I guess section of the grid, if that makes sense.
Okay, thank you very much, Kaylee. So another question from the same person. For the grid diagram of 2D RZ, what are the mechanical boundaries of the core pellets? The core pellets seem to be hanging in the air.
Yes, so the pellets, essentially the way that it's modeled, and again, the BISON website, the documentation actually goes through all of this in depth. But essentially you're pinpointing, if you can see my cursor, yes. Essentially you're locking down the bottom left corner of the fuel pellet, as well as the bottom left corner of the cladding. You typically set a kind of locked in point and set those mechanical boundaries as 0. So when we're modeling swelling and the fuel kind of expanding outwards radially or expanding axially, that's your pinned location for the fuel rod. I think hopefully I'm understanding that question correctly. And then generally we can calculate or approximate neutron flux and neutron fluence through the cladding here. And that's essentially the way that we do that. Hopefully, again, that makes sense.
Thank you, Kaylee. I do not see any more questions. Just thank you from one of the participants. So if there is no question anymore, I would like to thank you very much, Kaylee. It's a really, really nice presentation, very inspiring for a lot of people. I would like to thank you also for volunteering to present. It's not easy, your first year PhD student. So my admiration to you. And everyone, you have the email of Kaylee at the beginning of this presentation, which is going to be available on the GIF portal. So if you have other questions, feel free to contact her. It's a small community, so at the end of the day, we know each other. So do not hesitate. And Kaylee, again, thank you. I wish you the best for the rest of your research and your PhD. I know you will do very, very well. So with that, we see you soon at the end of July. Thank you again, Alexey, for organizing this webinar and hosting this Zoom webinar platform. Thank you so much, everyone. Wherever you are, we wish you a very good day or a good evening. Thank you again, Kaylee. Bye-bye, everyone.
Hi, everyone. Thanks so much for having me.
Thank you.
Thank
Bye,
you.
everyone.
Bye-bye.